confidence interval for a proportion. In a random sample of n equal 100 patients, the proportion cured by a new drug, p hat, 60 over 100 or 0.6. This is taken from a larger population, population of millions of patients. In that population, the proportion that would be cured by the new drug, represented by the letter P, is unknown. We're going to find a 90% confidence interval for the proportion of patients that would be cured by the new drug in the long run. So in this sample, the proportion cured was 0.6, but that could have happened by chance. The population, the sample proportion will vary from one sample to another. So our best guess is that 60% will be cured in the population, but we don't know that for sure, and we want an interval such that we're pretty sure that the proportion cured will be between the two numbers of that interval. The exact probabilities will be sort of based on binomial probabilities. It's not exactly a binomial, but it's related to binomial. But those probabilities involve quite a bit of computation. We're going to see if we can use normal approximation. We want to check that n times p hat is at least 5. 100 times 0.6 is 60. That's at least 5. That's a yes. N times q hat is 1 minus p hat. That's the proportion not cured. 100 times 0.4 is 40. That's more than 5. So that's a yes. So that means we can use the Z table to approximate. Okay, so we want a 90% confidence interval. So 1 minus alpha as our level of confidence, it's 0.9 as a percent. In the WebAssign exercises, sometimes they ask you to fill in the blanks on a graph like this. The CL is 0.90. Our level of doubt, if we're 90% confidence, that means we have 10% doubt, or alpha. So alpha is going to be 10% or 0.1. Alpha divided by 2, 0.1 divided by 2 is 0.05. And we want half of our doubt on each extreme. So we want to find out these z-scores here that will give us the 90% confidence in the middle. So our half of our level of confidence, 1 minus alpha divided by 2, 0.9 divided by 2 is 0.45. We look for 0.4500 in the body of the z-table using this table in reverse. And it's not in there exactly. The closest numbers are in row 1.6, columns 4 and 5. If we look at the last digit, it's equally close to those. If the last digit is off by 5 in either case. So it's going to be halfway between 1.64 and 1.65. And if we take the average of those, we get 1.645. So Z is approximately 1.645, and then on this end it's going to be a negative 1.645. Okay, so then now we want to find the X scores that are the P hat scores that go with these Z scores. So the lower bound is going to be Z minus P hat minus Z times the square root of P hat Q hat over N. So it's going to be P hat is 0.6 minus 1.645 square root P hat is 0.6, Q hat is 0.4, sample size is 100. .6 minus, and then if we put this in the calculator, 1.645 second square root 24 divided by 100, 0.08. Okay, and I'll put that in the calculator. That's I computed this part after the minus sign separately because sometimes it's reported separately. If we subtract, I'll get 0.5194. Uh, 11787. So this piece here is the margin of error, or it's also called the error bound, or sometimes just the error. Sometimes it's abbreviated EBM or E or something, and that's sometimes reported separately. Okay, the upper bound is going to be the same formula, except we're going to have a plus sign in the middle here. So it's going to be 0.6 plus 1.645 square root 0.6.4 over 100, 0.6 plus 0.080588213, 0.680588213. So that's so if we round this off, this is approximately 0.52, and this one is approximately 0.68. So that means we're 90% confident that the proportion cured by the new drug in the long run would be between 0.52 and 0.68. So that's an interval estimate. So that our point estimate for P, the unknown proportion cured by the new drug, is 0.6. But now we have an interval estimate. We're pretty sure that P is between 0.52 and 0.68. And the margin of error, we report that separately. Sometimes they ask for that separately. It's approximately 0.08. It's approximately 0.08. That's how much we can expect to be off by. And it's also called the error bound. Okay, some comments here. The sample proportion is a point estimate for the unknown population proportion P. Sample proportion will vary from one sample to another, but on the average will equal the unknown population proportion. The 90% confidence interval is an interval estimate. 90% confidence will vary from one sample to another, but 90% of the time will contain the unknown population proportion. The margin of error, E, 0.08 milligrams per deciliter, or error bound, also called sampling error or just error, tells us how far our point estimate can vary with 90% confidence from the unknown population proportion. And a good but possibly expensive way to decrease the margin of error is to increase the sample size, and the cheaper way would be to decrease our desired level of confidence. But the bottom line, if you want a more precise estimate, you need a larger sample. Okay, so so for that reason, because of the trade-off between sample size and getting a more trade-offs involving a larger sample size. On the one hand, you get a more precise estimate. On the other hand, it's more expensive to take a larger sample. So that for that reason, sometimes it's good to know in advance how big you want to take your sample size. In this example here, pollsters wish to determine with 90% confidence the proportion of voters who support Joe Biden for president with a margin of error less than 0.03, how large should the sample size be? So this 9% confidence, that's the same level of confidence we used before in the previous example, and we have a z-score of 1.645 corresponding to that level of confidence. Because we don't know in advance what the sample proportions will be, we're going to estimate p hat is 0.5 and q hat is 0.5. That will give us an overestimate for the sample size, but probably it's better to be an overestimate is better than an underestimate. Anyway, we'll use that, and then we can fill in into the formula. So we want the margin to be less than 0.03. Less than 0.03, and the margin of error is what comes after the plus or minus signs in the formula. So this piece here is the margin of error, so that means that z times the square root of p hat q hat over n has to be less than 0.03, and z, for this problem, for 90% confidence, is going to be 1.645, and 0.5, p hat and q hat were taken to be 0.5, and we don't know. So we can multiply 1.645 times the square root of 0.5 times 0.5 to simplify this, and we'll have 1.645 times 5, you get 0.8225 over square root of n less than 0.03, and then we want to multiply to get square root of n out of the denominator, multiply both sides by square root of n. And on the left side, the square roots of n will cancel, and that will leave us with 0.8225 less than 0.03 square root of n. Divide both sides by 0.03, and that gives us 225. I don't have enough 2's in here. Divide by 0.03. Try that again. Uh, 27. 27.416666667 less than square root of n, and so these cancel, and then square both sides to get n by itself. So I'm going to square both sides to get rid of the square root. I get 751. So n is going to be greater than 751.6736111. Now, a 751 sample size of 751 is not going to give us our desired margin of error, or might not give it our desired margin of error. 752 will give us, it's a little bit bigger than what we need, but it's better to have an overestimate than an underestimate. So 751 point anything, even if 751.01 or something, 751 point anything, we want to round up to 752. So the sample size has to be at least 752 voters. Okay. And that concludes this presentation.